Fantastic, fantastic. Okay, well, that's wonderful to see so many of you here. We were betting with Nikita if we're going to have 1 or 2 people, but you exceeded all our expectations, so that's very good. And there was a talk before about using Apache Ignite with Postgres, and we're kind of having a little bit similar, but I would say a different talk about using Apache Ignite to really alleviate or some MySQL pains or accelerate it wherever you want. So the structure of this presentation will be the following, right? I am, but no ways, an Apache Ignite expert, so I will talk about my years of experience with MySQL and of the problems we see and what are kind of existing solutions we will have used for them. And then Nikita will talk about what Apache Ignite has to offer, right? So, pretty simple. Now, who am I? Well, I am founder of Percona, and for this talk, I think what is most important, I've been a MySQL user since 1999. So, oh my gosh, it's almost 20 years now, right? So, lots of experience since that was a very, very immature product. And really, I am myself very passionate about the open source database technologies and really about those data intensive problems. So as a Percona, we're a company which provides solutions for MySQL, MariaDB, and MongoDB. So we provide support, managed services, some consulting and training. And what is our sweet spot is, while we have certain, we develop certain software, we really provide multi-vendor support in and out of the cloud, right? So we don't really require you to run Percona software. If you go to MySQL or MariaDB or Google Cloud SQL or maybe Amazon Aurora, we get you covered across all that variety of platforms. So we have also created a lot of open source software for years. And for that, the reason for that was because a lot of problems we ran into, they couldn't be really solved by, well, just advising people alone, right? So lots of software, and all of our software is open source. We don't have any special enterprise version. And kind of on the contrary, when we look at Percona server for MySQL or Percona server for MongoDB, what we have in our software is number of features which only exist in enterprise version of theirs are available as in open source edition of ours. What I think is specifically relevant for this audience is what we have the Percona memory engine. Some of you may attended Vadim Tkachenko's talk yesterday where he spoke about that kind of in a little bit more details. But this is basically the storage engine, a way to store data in MongoDB, which allows you to store all the data in memory, which gives you A, much better performance, and then B, it also comes with a lot more predictability, right? You can see this graph is not a lot of this kind of, performance kind of jitter back and forth, which comes with using the standard WireTiger disk-based storage engine. Now, when it comes to technology, I have like a very simple conviction: is that there is no silver bullet, right? Wherever we develop technology, we have to do some choices, and that means trade-offs, right? If you say yes to something, you have to say no to other. And MySQL, in this case, which I have a lot of experience on, is no exception. Now, I think another interesting point in this case, or another general trend, is what if you look at many large-scale applications, then they are going to use more than one technology, right? Some of you may have heard this term called polyglot persistence, when people would say, hey, we are going to use multiple technologies which are good, each of them good for their own purpose, right? And I think that is a fantastic way to develop applications, but of course you have to be a little bit careful here as well to make sure you don't create a very kind of big zoo of technologies which is very hard to support for for your team. I remember in my experience, there was an interesting use case where I would come up to a company, and they had like some very passionate developers saying, oh, you know what, we should not be storing our logs in MySQL because, you know what, Cassandra is great. Cassandra is eventually consistent. It's really designed for those kind of writes. And I would tell, well, how much logs are you speaking about? Right? Because maybe, you know, that's like millions or billions of records a day. And he would tell, well, it's about 10,000 log entries. And I would say, well, you know what? At this point, you can really stack it to pretty much anything you like, right? You can stack it into the files and use grep over years, right, with pretty much, you know, seconds of response time. Well, anyway, the long story short, I visited those guys again in maybe like 6 months or so, and we came to look at the log file for some reason. And they told me, well, you know what? We actually have a problem, right? Our log files are going to Cassandra as the developer wanted. But because he left, we have no one left who knows how to get that data back from Cassandra, right? So that may sound funny, right? Because of course we are obviously, you know, anyone can probably figure out how to get the logs from Cassandra in a relatively short period of time. But the point is what you have to be ready, obviously, to operate the large-scale systems. Now, I think this things using multiple technologies is especially easy and also some kind of dangerous with the open source. Because if you would want not only to use, I don't know, let's say like Oracle, what your company use, but also add, you know, Microsoft SQL Server to that, then you would have to, well, you know, get a budget for that, right? Now, developers are kind of empowered to go ahead, download any kind of stuff they like and play with it, right? So it's very easy to prototype and test without talking to anyone. And often with open source, we may find some technologies being used by developers when it's kind of, well, too late to make them not used, which can be a problem, but I think that also has been a very reason how many open source technologies became successful, right? I know with MySQL, if everybody would have to be asking permission to MySQL to use MySQL in the environment early years, right, it's never would have gotten to the level of users right now. And I think another piece which is very interesting is that I think the open source community is very good at building bridges and actually seeing how those different technologies can be used together, right? Like we are talking about how Ignite can be used on MySQL. There is some other folks talking about the same with Postgres. You don't see a lot, for example, how Oracle and Microsoft SQL Server can be used together, right? I mean, because there is a lot of competitions out there, and there is not a lot of kind of community with access to the source code that actually can make interoperability better. Okay, so we spoke about the balance already. I kind of covered that a little bit ahead of that of the slide. Now, let's talk about the MySQL more specifically. So, as I mentioned, my belief is MySQL is good for many things, and you would find many famous companies, especially here in the Bay Area, using MySQL as a primary data store. You know, ranging from Facebook to Twitter, Uber, but it is also not exception. It is not good for everything. And here are few things which MySQL has a problem with. So the first one would be hot data. A good example of a hot data is something like you have a cache which you get a very quick access to, like large volume of very simple requests. And in this case, when you're using MySQL, you have to pay the overhead through the SQL. Because SQL, that is a relatively complicated language, you have to parse. There is also some other overhead with permission checks and so on and so forth. There, you would not ever be able to get as good performance of that as with some more simple protocols, right? And also, MySQL does not really have very good memory-focused engine. If you look at this case, the majority of in-memory workloads of MySQL would use kind of standard disk-based InnoDB storage engine, which is good in memory, but it's not very optimized specifically for in-memory standpoint. There is other storage engine called memory. It is not very robust, right? It has table level locking in turn, doesn't have a very good concurrency and so on and so forth. And then finally, MySQL itself is not really designed very well for very high concurrency. So MySQL can handle hundreds or even kind of thousands of concurrent connections, but not really, really more than that. And in some applications, especially when you have a kind of spikes of very large amount of concurrent requests, MySQL basically crumbles, right, in terms of how much logging has to happen internally. So what solutions have existed for those problems for years? Well, one, if you are in MySQL itself, allows you to do certain things to make it better. MySQL has a Memcache compatible interface, right? So you can access the data in it through Memcache protocol, right? And in this case, you bypass SQL and bypass some other restrictions. You can also use tools like a thread pool, which allows you to manage successfully much larger number of connections, right? So for example, if you want 20,000 concurrent connections, something like that, that can be managed through a thread pool. And there are also some external solutions which has been used for many, many years, right? So if you look at a lot of those kind of large companies I mentioned, many of them would be using Memcache or Redis to supplement MySQL, right? You would like Facebook is particularly famous in that. I think they did a lot of very fancy work in making Memcache to operate with MySQL for last I don't know, probably close to 10 years now. Now another concern that you may have with MySQL is a highly volatile data when you have a lot of updates, especially hitting the single row. And in this case, that is not surprise because MySQL is really designed to be kind of fully transactional ACID semantics. That really comes with a substantial amount of overhead, especially if you think about the disk-based durability, right? So in MySQL sense, if you are committing the data, it should have to be persisted and in memory, which is done through their disk-based log. Also, what MySQL does is a pessimistic locking, right? So that means if you have a very hot rows which are being, concurrently modified, then you are very likely to have some contention which are going to limit that. Now, what can be solution? Well, some of them come from the data design, right? You can design the data in a ways you avoid creating a hot rows. So for example, right, the kind of a classical example would be if you need to maintain the counter, instead of having one counter row, you can create and say, have a 10 counter rows, right? When you update sort of random one of them and or something like that, and then you sum all those counts if you have to get a count, right? You can do many of those things. There are some configuration tuning you can do, right, to alleviate their contention. And another interesting problem what MySQL used to have, which may not be kind of obvious from previous slide, is for years, the amount of writes MySQL could take was not limited by writes, but by amount of data you could replicate, because the replication was happening through a single thread, right? So if you put too much load on the master, your slave can just never catch up. In a new version, you can deploy parallel replication where that problem goes away. And again, if you look at our external solution, it's again pretty much the same, similar in-memory solutions, right? Where we can store the hot data in those technologies and then sort of periodically persist that in the MySQL database when you have to. Another concern is large data volume. MySQL out of the box has been designed for a single node system, right? Which, as in any single node, it's limited in a CPU and amount of memory you can have. Now, if you look at any large-scale applications, like the ones I mentioned, like a Facebook, of course, they're not running single, MySQL system. There is no, computer out there which can run a whole Facebook, right, on the same single operating system image. All those guys use sharding, but sharding in MySQL is kind of painful and complicated, especially if you are looking for complicated queries which span multiple shards. So what solutions have been in this case? If you look at their MySQL space, you are seeing many manual sharding solutions, especially applications which 5 to 10 years ago using MySQL. Almost all of them have some sort of manual sharding in place. There are also some up-and-coming solutions for MySQL which make sharding less painful. One I find very exciting is Vitess. Vitess is something which was designed by YouTube team at Google, right, where they moved a lot of applications on that. And I see recently the Slack folks, they also said that they have migrated some of their data to Vitess, which is very, very exciting because you know what? Your baby is always the most beautiful, right? So then YouTube guys saying, oh, Vitess is kind of amazing, but nobody but YouTube actually using that, then that doesn't give me a lot of confidence. When I'm seeing some other big companies being successful using that, that is a completely different story. And ProxySQL, that is the proxy and kind of traffic management solution of MySQL, which also can be allow you to solve some of the sharding problems. Now, if you look at solutions outside of MySQL, of course, again, we can use some of the same supplementary technology, right? And various ways you can shard the Memcache, and especially with Redis from Redis Labs, right? We have a lot of scalable solutions out there. But a lot of folks would simply say, hey, you know what? Screw the MySQL. It's too painful. Let us go web scale, right? And use solutions like MongoDB or Cassandra, where sharding is built in, right? And yes, we have to give up this kind of stupid SQL, but you know what? Many new generation developers, they didn't like SQL to begin with, right? I mean, they kind of think there's only one language, and that language is JavaScript, right? Oh, JavaScript. So yeah, you can find a lot of especially front-end folks, right, which that's the way they operate. Okay, and then the analytics. So MySQL has a lot of restrictions here. Like, it doesn't really have any column-based storage engine. Its optimizer is relatively limited for complicated queries, though I would say in MySQL 5.7 and MySQL 8, this is kind of getting a lot better. But I think it's the most important two things is that the MySQL does not do parallel query execution, like using multiple CPU cores to serve at queries, or massively parallel or distributed query execution, which is absolutely required if you are doing some analytics on substantial scale. So with MySQL, you can do certain things in terms of configure that, get a bigger box, maybe do some schema design here and there, like adding covering indexes or using appropriate storage engine, but you never get too much mileage out of a single MySQL box just because, well, there is not only so much power you can get from processing data on single CPU core. And they see a lot of external solutions here. Obviously, Hadoop and Spark are very common ways, right? People are replicating the data from MySQL and other systems kind of, and processing that if that's ecosystem. Vertica has been also pretty popular for more of like real-time SQL queries. And recently we see some good traction with folks, especially those who have been adopting Vertica before, replacing that with ClickHouse, that is kind of relatively new massively parallel analytic engine. And they also have another solution out there called MariaDB Column Store that allows you to do analytics using MySQL protocol, right, and most of the MySQL functions. Okay, the next one would be our full text search. Full text search in MySQL is also not great, right? To be frank, it kind of works if you just look in very light duty full text search, like maybe, hey, I have WordPress with a couple of thousand posts and comments. That works, but even if you're really taking that to any substantial scale for millions or hundreds of millions of documents, MySQL full text search doesn't scale. And again, there is no limited processing. It's really kind of really relatively simple add-on. There is no relevance, no good relevance functions, and so on and so forth, right? Or no good language support, like stemming and other things. So if you look at what solutions out there, for small-scale applications, MySQL works, especially since in MySQL 5.6 full text search works for InnoDB tables as well. Now, if you look at really any large-scale full text search application, those workloads have moved to other data store systems like Elasticsearch, Solar, or Sphinx. I think these are kind of the most commonly used systems. If I think Elastic is by far being leader in this space. Okay, so these are kind of a common systems which we see a lot in the wild today. Now, I believe, however, is what the thing about the technology. If there is a constant change in the new technology, constantly appears, and you should be obviously on the lookout for the new ones. Now we have Nikita to talk about one of such technologies which also can be used instead of Memcache, Redis, right, and some other technologies I've mentioned, and come with some additional benefits.
All right. Microphone?
Oh yeah, that's fine. I wasn't sure if you're going to use it as well, or if you're going to.
Can you guys hear me? Excellent. Hold on a second. How about now? Perfect. So first of all, great for sticking up for the last presentation on the last day. I know it's hard. A lot of people flying out. So listen, we only have about 15, 20 minutes. So I'm not gonna give you the whole presentation about Apache Ignite. We'll go pretty quickly. So some of the kind of key elements, what it is, and how do we actually work with the SQL world. It's really interesting. When people think about something like in-memory computing, which is Ignite, it's not really a replacement for SQL databases. Most of the time, we work with them. It's rarely when we just completely wipe out one type of technology and replace with another. It's always some kind of combination of it. So what is Apache Ignite? Again, there's plenty of talks in this conference and elsewhere, but very quickly, it's a memory computing platform that combines essentially lots of different technologies into the one platform for in-memory processing and memory computing. Today, Ignite really has a full SQL support. We have a full NoSQL support with a key value, transactional key value store. We have streaming. We have a Spark Hadoop integration. We have even fairly esoteric things like we have in-memory file system built into it. So really, the idea behind Apache Ignite, it's a fairly old project. The first line of code was written in 2005. It's a fairly old code base. The idea behind Apache Ignite was always to create this kind of an overarching framework for any use cases, for any application for in-memory computing. And we'll talk a little bit more. So we provide a durable, strongly consistent, highly available store and a processing system. It's a fairly confusing picture, but I'll peel it off a little bit in the next slides. So when we talk about in-memory computing, what's funny enough that over the last couple of years, we kind of moved away from talking about in-memory computing to start talking about a memory-centric computing. And there's a good reason for that. If you heard the Abe's presentation in a keynote, he actually explained it very well. An idea that, we all kind of, in-memory computing by itself is a very old technology. It's always funny to remember that, back in the 50s, we had in-memory computing, right? The first time we ever created a tape drive or a disk, we always had a small cache somewhere where we kept just a few bytes, just a few kilobytes, and a fewer, more and more and more over time. But we always had this in-memory processing. The memory was way too expensive, it was way too small, it was one computer and whatnot. So and then essentially we got to the point of probably whatever 5 years ago when everything again got haywire, and we started doing in-memory everything, right? And very quickly, the industry kind of hit the wall that we cannot really fit anything, everything in memory, right? The data growth, outpaced dramatically our capability of growing the memory of a cluster. And we started hitting hitting problems where, well, how do I store my quarter petabyte in memory? Well, you can physically, but it's awfully expensive, in many different ways. And so we start talking about a memory-centric computing versus disk-centric. And that's actually a very nice and cute way to kind of disambiguate the whole idea. For in a disk-based computing, which is something we've been doing for the last 60 years, we use disk of a variety of block-level devices as a main storage. And we use cache, essentially RAM, for caching, for storing frequently accessed pieces of information. We don't have to go to a slower external block-level device. We've had this technology for literally 60 years by now. So the memory-centric computing has really, in many ways turned this upside down. We're starting to use memory and new types of memory as the main storage of data, and only use disk or block-level devices for essentially backup and overflow when something doesn't fit in RAM. We actually have a kind of cute way of saying this, that caching versus stashing. You cache in the disk world and you stash the data away from RAM to the disk in memory-centric world. Now, you may be confused a little bit why it's so important to talk about it. Well, because it seems like both worlds kind of move in the same direction, right? And that's what Abe mentioned in the keynote, is that there is definitely a difference. Because in the disk-based or disk-centric computing, you always optimize for block-level devices. Those external devices, they're block-level, they just have their own world of optimization algorithms. And the minute you start optimizing for a byte-addressable RAM, right? RAM is byte-addressable, has very unique characteristics, right? Reading the 1 byte or reading 2 bytes is different than RAM. Reading 2 bytes is twice as slow as reading 1 byte. As you probably all know, reading the disk, whether you're reading 1 byte, 2 bytes, or up to a kilobyte at the block level, it's the same speed. You have a completely different optimization. Yet another interesting aspect of a memory-centric computing, which a lot of folks don't realize at the beginning, is that memory-centric is always distributed. I've been speaking about this subject for almost 15 years by now, and it's always, amazed people. Why the hell you talk about distribution when we're talking about a memory? And if you think about it in memory computing, how it progressed over the years, what's interesting is that distribution, or parallel programming, or distributed programming, any way you want to call it, was an absolute necessity for early in-memory computing systems. What's really interesting is that most of any in-memory computing system today are one of the most advanced distributed systems in existence because we had to do it. If anybody remember, mid-90s, how many kilobytes of RAM can you fit in one computer? Literally, maybe a megabyte, maybe a couple of megabytes. So it wasn't enough for anything, right? So back in the 90s, back in the 80s, as a matter of fact, at the beginning, people were forced to clump together a bunch of computers in a cluster to really aggregate as much RAM so you can have any usable amount of RAM. If you talk to folks from Wall Street, they'll tell you basically that in the late 80s, most of Wall Street clusters were about in-memory computing. They were first to basically, adopt this technology for trading, for currency exchanges and whatnot, where speed is essential. They were the first one to basically cobble together hundreds of computers. Remember, late 80s, hundreds of computers through scotch tape and chewing gum somehow to really kind of, ability to get all this memory kind of, combined capacity. So what's interesting is that in-memory computing systems today are one of the most advanced distributed systems in the world. For example, I'll give you, Apache Ignite routinely runs on clusters up to several thousands of nodes. You can hardly find any other system apart from maybe Hadoop and maybe Cassandra who has the same scale, proven scale. It's fairly complex to run a multiple thousand nodes in a cluster in a full transactional topologies and whatnot. So that's a testament that it's not like we're smart enough, but it's basically this whole technology was, driven by a need. Another interesting aspect of in-memory computing and kind of an offshoot of distribution is what's called a collocated processing. It's a very simple idea. I'll explain it to you. Probably most of you say, Jesus, we're doing it obviously the same way. But you'll be surprised that we were not doing this way 15 years ago. So the collocated processing is the idea that when your data is partitioned, it's kind of makes sense to send the computation to that partition that has the data you need for this computation. Because otherwise, if you don't do it, you send it randomly to some different node in the cluster. This node will have to fetch this data from a different node, process, and you have a lot of noise traffic and very complex problems. So in a collocated request, the request comes into the client node, and what happens in the client node, essentially client node sends the computations to the data. Think about this very carefully if you haven't heard about it. It sends computation to a data. It doesn't send data to computation. It's a very fundamental idea behind any distributed collocated processing. It has very interesting properties. Computations don't change as frequently as data. Computation is a lot smaller than data. If they don't change, you can cache them very effectively locally. So it's a very proper way of doing distributed computing with essentially collocated processing. So you send the computations to each node. Those computations run in parallel on each node. So you don't overload a single client node with all the data and all the processing that needs to happen. So the server nodes in this example will send back just the partial results, and the only thing that client node has to do is aggregate those partial results. For most of you, it sounds pretty reasonable, logical, because by now we all know how to do it and we're doing this. Believe me, literally 15, 20 years ago, that's a fairly new paradigm. And in-memory computing, because of its distribution roots, everything is based on this idea. I'll talk about SQL and how we do SQL and how we do this. That's the fundamental idea of why we do SQL so well in distributed fashion. Well, not only SQL, basically any type of processing we do based on this fundamental idea, and that's what gives us a fairly linear scale on the performance. So what do we do essentially as far as SQL capabilities? Again, I'm not going to bore you with long definitions of what we do as far as rest of the functionality. But in terms of a SQL, like in Ignite, we're actually one of the few, if not the only, in-memory computing platform with the full SQL support. This is one of those cases where we're obviously not going to be as good as, let's say, MySQL in terms of a SQL, but I think we're reasonably 70, 80% there as far as the support for SQL and whatnot, which is fairly good, believe me, for a non-SQL database. We're not positioning ourselves as a SQL database, but we have fairly good SQL capabilities. So we have what's really unique about us versus, for example, MySQL in the sense we have a full support for distributed SQL. Just like, for example, Google Spanner, Google Spanner, that's another kind of system that's very close to us. So we have a distributed SQL, essentially database capabilities. We both work on RAM and disk. Remember those, memory-centric. It's not only memory. It's a combination of memory and the disk, and you can basically vary this balance between you through your configuration. So we ANSI 99 compliant, not fully, but I would say 90+ degree there. We ACID compliant. We support full transactional behavior if we need to. Naturally, through our core platform, we highly scalable. I mentioned 1,000 nodes, and you can deploy this anywhere. What's really cool is that we provide you both ODBC and JDBC drivers. So you can talk to Ignite. Think about this, what Ignite is, right? It's an in-memory computing, storage, and processing system, right? It has a key value, it has a file system, streaming, Hadoop, blah, 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 blah. Yet, you can open up any tool that supports ODBC and JDBC driver, connect to it, and just work through a normal JDBC, ODBC connection, through normal SQL. Pretty cool stuff. Another way we work with, and that's actually what Peter mentioned, we can definitely speed up an existing MySQL installation, and that's actually a big chunk of what we do, because we're not coming to the customers, people not using the Apache Ignite just, hey, let us replace Postgres or MySQL. That's typically not what's happening. They already have infrastructure in MySQL, and they're looking for specific use cases. Where can we actually speed these things up? Like Peter mentioned, those memcached or Redis use cases. We're obviously way more advanced than those systems, and that's where we can help a lot. We can essentially slide in between MySQL and the application, and really provides you this kind of sophisticated and pretty advanced caching layer. No rip and replace, right? You don't have to change your database, which is typically a big deal. You can keep data both in RAM and MySQL. What's really cool is that unlike MySQL, like Peter mentioned, Ignite can scale to hundreds and thousands of nodes. So that gives you a very nice scale-up elastic layer where you can keep your database as it is, right? Don't really make any hard changes. And you can keep your data in this elastic layer of Ignite that can scale up and down as much as you like. We had all the basic read-through and write-through behavior, so you can basically talk to us, and if data is not in Ignite, we'll fetch it up from MySQL and keep it in a warmed cache in Ignite. So another interesting point is that, let's talk about SQL queries. What's really unique about us, about Apache Ignite, that's actually fairly unique. It's very rarely where you can say fairly unique in today's industry, and we are in this sense. There's only a few products that support, neatly distributed joins. And most of you, if you guys work with SQL world, you guys know that SQL was never designed for distributed joins because you have basically index explosion. It's hard to do the distributed joins. So we have two ways of doing SQL joins. We basically support both collocated and not collocated joins. In a collocated joins, which is this picture, I think, we essentially rely on the fact that data will be collocated. So when we essentially, if you think about the star scheme, we have a metrics and dimensions. Dimensions has to be replicated on each node, well, it's actually, as a matter of fact, I'm like a little bit confused. It's a little bit different approach we support as well. So we can support star schema joins, but those essentially work anyways. But in a collocated scenario, we essentially rely on the collocation of the data for this particular query. And if that works, our distributed joins would work extremely fast, just as they work locally. So if you can collocate your data, if you can essentially store your data in a collocated fashion for particular queries, those distributed joins would work blazingly fast. And that's a pretty big deal because one of the reasons that you don't see Oracle, for example, on hundreds of nodes is because it doesn't work this way. It's very hard generally to do, it's impossible, as a matter of fact, it's not hard, it's impossible mathematically to do a arbitrary distributed joins in any effective way. Which we also don't support, but the coolest thing, we're not going to blow up. Those joins that are not collocated will work the same way. They're just going to work slower, just as we cannot change the laws of physics. It's just going to work slow, but they will work. Obviously, if we have terabytes of data, it may take hours to process it because of a data exchange. So if you look at the picture, right, this previous slide and this slide, that's the only dotted line exists in the difference, right? Because if you have a non-collocated scenario, the data have to be exchanged between nodes, and that's the major point of slowdown. So once you have this dotted line anywhere in the architecture or in the kind of execution flow, you're done as far as performance, because data exchange is the single biggest killer of performance here. So the really cool thing, again, is that we support both ways. If your data is collocated, we're going to be automatically very fast. And obviously, it's not always possible. I would say frequently it's not possible to collocate all the data, but you can collocate certain amount of queries. If you know the queries, for example, are critical for performance, you can collocate data for those. And you can actually do a SQL query on hundreds of nodes very, very fast, pretty much in the same speed of one node. It's a very big advantage. As a matter of fact, if you guys want to kind of have a deep read on this, look at Google Spanner. We use exactly the same technology, almost to the point of being very similar in how Google Spanner works in the same scenario for us. We have a little bit different implementation of transactions. Google Spanner has its very complex transaction behavior with custom clocks and whatnot. We have different implementation, but from a user perspective, very similar approach.
Excuse me. So you're saying if the data is not collocated, you move the data so that it is collocated?
Yeah, we will have to collocate data by ourselves, and that will slow down dramatically. That's exactly how any naive implementation of SQL, distributed SQL, would work. Naturally, it has a lot of pitfalls. If we cannot hold all the necessary data in one node, we're going to fail the query. It's just, we cannot change the laws of physics here. That's exactly why distributed databases never took off. I mean, SQL databases, because it's just, in a general case, it's an unsolvable problem. You have to shard, you have to partition, or you have to collocate. There's all these different techniques, but generally it just doesn't, it was never designed for it. If you look at the SQL algebra, it doesn't work. You have to have all the indices. In general case, you have to have all the keys for all of your overall superset of data. And if it exceeds your capacity to store it, you're done. There's no other way of doing this. There are some other ways, but we get the hairy details. Anyways, the code looks very similar. If you guys are familiar, this is the Java code on the left side. I think it's a PHP, or I think it's a Python, whatever. I'm not really good at it. So either one of them on the right side. So it's very similar. You can basically use your traditional, programming techniques, how you guys do this, coding on any language. It's a really cool thing, because although we're a JVM-based software, with our SQL capabilities, you don't have to use any of the JVM languages. As long as, again, you have any kind of JDBC or DBC driver connecting to it, you can literally connect to us as a SQL database and go from there. What really separates us, again, from a lot of different kind of, half-baked SQL solutions, we're not only supporting selects, right? We're supporting all the, all the DML, all the DL, most of the DL things. So you can really work with us as a normal database if you need to, right? You can select, create tables, drop tables, update, delete, whatever you like. Do whatever you like. So this piece of code on the right, just demonstrates that. It's actually a very interesting point. So we're really the only system in the market, the only project on the market, if you will, where you can literally create table through a SQL and then use a NoSQL key value access to the same data. Think about it. Or vice versa. You can create, data through a file system API or a key value and then access the same data through a SQL query. It's a very interesting thing. We have plenty of use cases in Apache Ignite where people actually use a NoSQL capability, like a key value access, right? Normal key value transactional. And then they use SQL only where they really want to avoid the full scan. Peter mentioned that people hate SQL, but most people don't realize the minute you need to have a full scan, you're done in a normal system. Imagine you have millions of employees. How are you going to do, find me all employees with the name Nikita, first name Nikita? If you don't have a SQL, which is indices, you're done. You're going to be scanning, for minutes and minutes. So unless you have indices somehow, but then once you have indices, you have to have a SQL, right? This is the language that was designed, 40 years ago, specifically for these use cases. So you have to have a SQL in the system because, unless you're basically constantly doing key value access, if you do anything more advanced than that, and most of us do today, you got to have some SQL capabilities. So, and we have a pretty interesting, support there as well. So a couple of last slides, again, really, really quickly. So Ignite comes with a nice web console. It's a basically notebook-like style interface. So you can run your SQL queries, you can see visualizations, you can do whatever you like. It's a very typical analytical notebook interface. If you don't like ours, you can use Zeppelin, Apache Zeppelin. We have full integration with Zeppelin, so it's the same basically what Spark has in one way or another. So you can use all kinds of tools. Don't like this, you can use something like Tableau. We have full integration with Tableau. So you can essentially connect Tableau to the Ignite and do all kind of, data analysis, data visualization. So, and that's not just a few examples. Obviously, with JDBC or DBC drivers, you can connect any tools to Ignite and really use it. So the bottom line is that, as Peter mentioned, technologies are evolving, and MySQL is here to stay. Ignite is here to stay. There's use cases where, many use cases where we work very nicely together, where you can retain your database. You should retain your database in many cases because you have other business processes around it. But then you can add Ignite to it and eventually move some of the use cases to Ignite entirely because Ignite really gives us this, a tremendous speed and scale just by nature of how it was designed and what it's for. So, thank you very much, guys. It was a last presentation on the last day. Thanks for sticking up and sticking out for this. And I think we have the last talk in a big audience. I think the closing remarks after that. Thanks a lot.